Welcome to today's webinar. Today we will show you how to design a step foundation in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Global Software. For instance, the German and English webinars, technical content of the website, and so on. I will be the moderator today and I will answer your questions together with Ann-Kathrin Danwert. The presentation will be done by Hedi Bukra. Both of my colleagues are members of the development team Concrete and also on the customer support team. You can ask questions when you press the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email questions to info@global.com. Okay, that's for the moment all from my side. I hand over to Hedi. Hedi, it's your turn.
Thank you, Andreas, for the introduction. I'd also like to welcome everyone to today's webinar. In this session, we'll look at the design of a stepped foundation in RFEM 6 from both the reinforced concrete and the geotechnical perspective. We will use a typical hall structure as our example, allowing us to demonstrate each step in a practical context. We'll start by modeling the stepped foundation in RFEM. Then we'll see how rotated foundation geometries can be modeled cleanly and efficiently. And after that, we'll define the load cases, the load combination, and the additional loads that act directly on the foundation. And next, we will focus on the soil and show how to model a multi-layered borehole. And based on that model, we'll perform and evaluate both the reinforced concrete and geotechnical design checks, including a look at the graphical representation of the results. And finally, we'll take a look at the printout report, which documents the entire design process. With that overview, let's now switch to the software. For today's webinar, I've already prepared the whole model in RFEM. And before we move on the actual foundation design, let's take a brief look at the model so the relationship between the structure and the foundation is clear. This is a mixed construction hall. The columns and the roof girders are made of reinforced concrete, while the purlins between them are steel members. The hall has two outer rows of column along axis A and B. These columns have a cross-section of 45 by 45 centimeters, and the inner columns are smaller with a cross-section of 25 by 25 centimeters. The foundation system is also varied. Under the outer column, stepped foundation are used with different geometries depending on their location. And under the inner column, simple isolated foundation are provided. And in today's webinar, however, we'll focus exclusively on the stepped foundation beneath the outer columns. Let's also take a quick look at the model base data, where the main default settings are defined. In the main tab, the model type is set to 3D. This is important because it allows the foundation to be analyzed spatially and to consider all load directions coming from the hull structure. In the add-ons tab, two add-ons are activated for this webinar. Concrete foundation, obviously used for the reinforced concrete foundation design. And then we have geotechnical analysis, which is required because we want to model a multi-layered subsoil beneath the foundations. And without the geotechnical analysis add-on, only a single soil layer could be defined. Now we take a look at the used standards in this model. Here we define the design standards used by the activated add-on. For this webinar, the most important settings are the standards for the reinforced concrete, and geotechnical design. Here, Eurocode 2 is selected for the concrete design and Eurocode 7 for the geotechnical design, both here, for example, with the German national annex. And then we take a look at the model parameters tab. This tab contains the location of the project, which here, for example, is in Tiefenbach in Bavaria. The location can easily be selected by clicking on the map, or here writing the address. And once it has been applied, RFEM automatically determines the relevant zone information, such as the snow load zone and the wind load zone. And this information is then available, for example, when the load wizard generates the snow or wind loads. Good. Next, let's have a look at the materials used in the model. The main structural concrete for the roof grinders and the columns, and also the foundation slabs, is concrete C3545. For the step of the stepped foundation, we will be using a C2530. The reason for using a separate concrete grade for the step will become clear shortly when we look at the construction of the stepped foundation in more details. For the reinforcement, a B500 with high ductility is assigned. And in addition, we have a structural steel material for the steel purlins. And now, besides the structural materials, there are 3 soil materials already here defined. These soil materials will later be assigned to the borehole to describe the layered subsoil beneath the foundations. Now let's move on to the foundation. In the concrete foundation section of the data navigator, you can see under single foundation all isolated foundations that have been created for the model. In total, we have here 7 foundation, 6 stepped foundation, and 1 pad foundation, which we won't cover in today's webinar. Several stepped foundation are required because their geometry and the additional foundation loads vary depending on their location. The names already indicate where each foundation is used, for example, here at the edge of the columns or at the different corner positions. In the concrete foundation add-on, a foundation is not assigned directly for a column or a node. Instead, it is assigned to a nodal support type, and every node using that support type automatically receives the same foundation. So this means that whenever 2 columns require different foundation geometries or different additional foundation loads, they must also use different nodal support types. And for this reason, a separate nodal support types have been created for each individual foundation. And here in the main tab of nodal support, we first define the support condition the usual way. An example here, the support is fully restrained. And to assign a foundation, here under option, the option foundation must be activated, and only then the additional foundations tab become here available. And here we assign the corresponding foundation for the nodal support. Here for the support type edge column A, foundation number 1, step foundation edge columns A is selected. And as a result, all nodes using the support type, in this case 5, 8, and 15, automatically receive the same foundation. Good. You may have noticed that most columns are aligned orthogonally with their foundation. However, 2 of the corner foundation are an exception here. This is due to an angled extension that connects the new hall to an existing building, and to align the new hall with the existing structure, these two corner foundations have been rotated in plane, one by 30 degrees and one by 60 degrees. And here also, that's why the model contains two additional foundation types, corner column rotated 60 degrees and corner column rotated 30 degrees. The rotation itself is defined directly in the nodal support. In the main tab here, the option specific direction is activated. And here in the specific direction tab, the type rotated via 3 angles is selected, and the required rotation angle is then entered, in this example 60 degrees, about the global z-axis. And here in the preview, it shows immediately that the local coordinate system of the nodal support has been rotated accordingly, and with it the orientation of the assigned step foundation. As an example, let's now take a closer look at the detailed definition of a step foundation. We will open the foundation below the edge columns in axis R, and in the Edit Single Foundation dialog box, all parameters required for defining and designing an individual foundation are combined. In the upper right corner, you can see the nodal support to which this foundation is assigned. In this case, it's nodal support number 1. The main tab contains the basic properties of the foundation. For the type step foundation is selected, and in addition to step foundations, the add-on also supports other foundation types such as pad foundations, pocket foundation, or bucket foundation. And below this, the material section, the concrete assignment for the step foundation is defined. Here, for step foundation, the assignment is defined into 2 parts. Material plate refers to the lower foundation slab, in this case C3545, and material 1, first step, refers to the step above it, here C2530. This separation allows us to use a higher strength concrete where it is required, and a more economical lower strength concrete for the less stressed step. At the bottom of the tab, we define the design properties section. And here, when the design properties checkbox is activated, this foundation is included in the design process. The geometry of the stepped foundation is defined in the geometry tab. The input is here divided into 3 main sections. The first section, plate, describes the lower foundation slab. It has dimensions of 3 meters in the x direction and 1.5 meters in the y direction, with a thickness of 50 centimeters. The second section, first step, defines the step placed on top of the lower slab. Its dimensions are 1 by 1 meters with a 40 centimeter thickness. The third section, column, contains the dimensions of the supported column. Here the values are 45 by 45 meters or centimeters, which corresponds to the cross-section of the edge columns in the structural model. These columns, or the column dimensions, are transferred automatically from the model. And below this, the base plate at column base option can be activated if a steel column with a base plate is placed on the foundation. And here the information graphic on the right provides a clear overview of all entered dimension, both in elevation and in plan view. I can also switch to the 3D model to view the geometry directly. And this makes it easy to check and understand the foundation dimensions at a glance. In the reinforcement tab, we define the reinforcement type used for the foundation. First, in the material section, the reinforcement steel is specified. And then in the plate section below, the reinforcement type is selected. And here 3 options are available: rebars, mesh, or a combination of both. For this example, rebars are selected. The concrete cover is defined in the next tab, concrete cover. The simplest approach is here to select the required exposure class according to Eurocode 2. And once an exposure class is selected, the add-on automatically determines the required nominal concrete cover C num. In this example, the resulting concrete cover is 30 millimeters on all sides. Of course, alternatively, the concrete cover can also be entered manually, allowing different values for the individual sides of the cross sections. In the plate reinforcement tab, the actual reinforcement of the foundation slab is defined. But before entering the reinforcement values, it is also helpful to briefly explain 2 important concepts behind this input. And firstly, understand how RFEM determines the required bottom reinforcement and what the distribution area in this dialog box represent. Here a short sketch to help to illustrate this. So this slide shows a foundation in both in the X and Y directions. The red line represents the moment distribution, and here the highest moment occurs directly below the column, while it decreases towards the edges of the foundation. And to capture this behavior accurately, RFEM divides each reinforcement direction into 8 design strips and 4 strips on each side of the column. And because the system is symmetrical, it is also sufficient to consider only one half with strips 1 to 4 here, for example. Strip 4 is located directly below the column, while strip 1 is located at the foundation edge. And for each strip, the required reinforcement is calculated individually. And for practical reinforcement definition, the strips are grouped into 3 reinforcement area, defined with x1, x2, and x3, and the same in the y direction. The second reinforcement area, x2 and y2, is located in the middle below the column. It covers 50% of the foundation width, perpendicular to the reinforcement direction. The first and third areas are located at the edges, each covering 25%. And these 3 reinforcement areas are the values that are entered in the plate. Now we come back to the plate reinforcement tab. Here the tab is divided into 2 sections, top for the top reinforcement and bottom for the bottom reinforcement. For both sides, the reinforcement can be defined separately in X and Y direction. At the top, a simple constructive basic reinforcement is provided, a diameter of 10 millimeters with a spacing of 25 centimeter is defined in both directions. And then for the bottom reinforcement, now we apply the distribution areas that we saw. And here for each direction, we can choose between 1 distribution area with uniform reinforcement over the entire foundation, or 3 areas with the arrangement that we saw. So in this example, 3 area option is selected. For the first reinforcement area at the edge, a bar diameter of 12 millimeters with a spacing of 50 centimeter is defined in both X and Y directions. The third reinforcement area on the opposite edge is identical to area 1. And for the second reinforcement area in the middle, the same bar diameter of 12 mm is used, but here with a closer spacing of 10 centimeters, providing here the higher reinforcement where the demand is greatest. In addition, the complete reinforcement layout can also be visualized. At the bottom right of the dialog box, there is the Show Reinforcement Layout button. A click opens a separate window showing the complete reinforcement arrangement. Here, for example, in a top view. And here you can see all important details such as item numbers, number of bars, diameters, and bar length for each reinforcement item. And for a clearer overview, individual reinforcement layers can be hidden. For example, the top reinforcement can be switched off to focus only on the bottom reinforcement. And the different reinforcement areas are also clearly visible in this view. And this view can also be saved as a template. Here we can give it a name. And then the save template can later be reused in the printout report, something that we will come back to at the end of this webinar. So far we have looked at the concrete side of the foundation. Now let's move on to the soil properties. Here the soil properties tab defines the soil beneath the foundation, and these informations here forms the basis for all geotechnical design checks. In the subsoil section, the subsoil conditions define whether the soil is considered drained or undrained. In this example, drained is selected. The definition type determines how the subsoil is entered. Here 3 options are available. Single layered, the simple case with one soil layer beneath the foundation. Multi-layered borehole, where here several soil layers defined through a borehole. This option we will be using today. Multi-layered soil massive, the soil or the layers are taken from soil massive created in the geotechnical analysis add-on. And here we select one of the boreholes already available on model. I have already prepared this borehole in advance. And here by clicking Edit Borehole, the corresponding dialog box opens. And the borehole definition here consists of 3 main parts. First, the location of the borehole is defined. In this example, the borehole is located at the origin. And here, important that the Z coordinate represents the ground level. The second part is the groundwater level, if required. The groundwater level can be entered here using the ordinate value. In this model, the option is deactivated, meaning here there is no groundwater. And the third part is the definition of the soil layers. Here the individual layers are entered in their order, together with the corresponding material and thickness. And the materials are selected here from the soil materials that we already created. And here on the right side, the borehole is displayed graphically. Now let's look at the additional soil parameters for this specific foundation. The angle of soil friction, this is particularly important for the sliding design. Then the angle of wall friction. Here it describes the friction between the foundation sides and the surrounding earth covering. The finished ground level value. Here it defines the final ground elevation. Then we have the earth covering with a thickness of 40 centimeters. This is it represents the soil above the top of the foundation. And here at the bottom in soil layers, the current soil layers is displayed. And as defined in the borehole, there are 3 layers, 3 meter gravel, 2 meter sand, and 4 meter clay. On the right, the resulting soil is here also shown together with the step foundation. Next, we look at the design configuration for the geotechnical and concrete checks. We start with the geotechnical configuration. This tab defines which geotechnical checks are performed for this foundation and which settings are used. And here, using the geotechnical design configuration field, a configuration is assigned to the foundation. In this case, configuration 1 is selected, and the settings are taken from the corresponding geotechnical design configuration dialog box. Here at the top, the governing design standard, including the national annex, is specified, and that means all design checks and partial safety factors are based on this selection. Here in the upper right corner, you can see which foundation use this configuration. Here it is assigned to foundation 1 to 6, meaning all 6 step foundations. In the main tab, here in the top, individual load components can be excluded from the design if required. This can be, for example, useful if a specific load component from the structural model should not be considered for the foundation design. And below this, the individual geotechnical design checks are listed. They can be activated or deactivated using the corresponding checkboxes. Ground failure. Here 2 calculation approaches are available. Use characteristic value of allowable soil stress. Here a user-defined value for the ground resistance can be used, and bearing resistance according to Annex D of Eurocode 7. And here RFEM calculates the resistance based on the entered soil parameters. And here the second option will be used. Sliding design check. Here the option consider passive earth pressure. It allows us, it allows the earth resistance acting on the foundation sides to be included. And consider resistance limit for undrained clay subgrade. It's a special rule that applies to undrained clay conditions. And then the remaining checks are equilibrium limit state, uplift limit state, here deactivated as we don't have groundwater, and then loads with large eccentricities and highly eccentricity loads in core. After the geotechnical checks, we now move on to the reinforcement concrete design. The reinforced concrete design checks are also controlled through the concrete design configuration. Here a corresponding concrete design configuration can be assigned. And here in the concrete design configuration, the first important setting is the location of the design section. Here for the bending design, the add-on needs to know where the governing design section is located. And for stepped foundation, 2 separate design sections are required because the reinforcement of the step and the reinforcement of the foundation slab are checked at different locations. And here, the first entry, first step, bottom reinforcement defines the design section of the step. Here through column edge, it's selected, meaning the section is located at the edge of the column. Alternatively, an offset from the column edge could be defined. And the second entry plate bottom reinforcement defines the design section for the bottom reinforcement of the foundation slab. Here through step edge is selected, meaning the section is located at the edge of the step. Also here, a user-defined position can also be entered. These two settings define the design sections used for the bending checks. Here the limitation of the neutral axis according to section 562. In this example, it is activated. Now we come to the punching sphere design. Here punching is activated, and here several additional settings are available. Define iterative critical section for foundation. So the critical parameter is determined iteratively by RFEM, but if this option is activated, the distance to the load area, LW_it, can also be defined manually. Factor for the relieving soil stress inside the control parameter, K_red. The soil pressure inside the punching cone reduces the effective shear force, and this factor K_red defines how much of this relieving effect is considered. And here a value of 1 means the full relieving effect is taken into account. Applied method for determining load increasing factor, beta. Here we have 3 options: full plastic shear distribution, constant factors, or user-defined. Here, minimum bending moments according to section 645 of the German National Annex, here deactivated. And at the bottom, 2 additional constructive checks according to section 921 are available, minimum and maximum reinforcement. Both here also deactivated. Good, and this completes our overview of all relevant properties and settings of the stepped foundation. Let's now take a quick look at the defined loads in our model. A total of 5 load cases are created. Load case 1, self-weight. Load case 2, live load. Load case 3, snow. Load case 4 and 5, wind load. The self-weight of the structural members is automatically considered by RFEM when activating this option. In addition, there are 2 further loads applied in load combination 1, which is the roof finishing load and the facade load. Both are generated using load wizard member loads from area load. The roof finishing has a load magnitude of 1.25 kN per square meter and is applied on the steel purlins, while the facade load is applied to the columns. Load case 2 contains also a variable roof imposed load of 3 kN per square meter, also using the member loads from area loads. And the load case 3, snow. The snow load is generated using the snow load wizard, here for a flat monopitch roof. And here in parameters, the required snow load zone is automatically determined from the location defined in the model parameters. Load case 4 and 5, the wind loads, also generated using the wind load wizard. One load case represents the wind in the X direction and the other in the -Y direction. Here as well, the corresponding wind zone is automatically taken from the stored project location. Let's get back to the load case 1, self-weight. And here The self-weight loads case contains one additional setting that is important for the foundation design. In the self-weight section here, there is a second option called self-weights for concrete foundations. The reason for this separate option is that the foundations created with the add-on are not modeled as a regular finite element members, and their self-weight therefore has to be activated separately. So after activating this option, here an additional tab becomes available, and here 3 additional effects can be considered in this load case. The first option is active self-weight for foundation structure. This includes the weight of the foundation itself, meaning the concrete weight of the foundation plate. The second option is active earth covering. This considers the soil above the top of the foundation. And if this option is activated and the soil properties and the earth covering thickness are defined in the soil properties tab, here we have a thickness of 30 centimeters. In this case, RFEM automatically generates this load automatically. So no manual load case entry is required for the earth covering. The third option is active groundwater. And here, when activated and when also a groundwater level is defined, RFEM automatically generates the corresponding uplift load. The automatically generated earth covering loads can be found here in load case 1 under additional foundation loads. This is the generated earth covering foundation load with load type earth covering. You can see it here also in the model. The groundwater is in this case empty. And in addition to these automatically generated loads, there is also manually defined foundation loads. And these line loads represent the self-weight of the whole floor slab, which sits on the single foundations. And the floor slab only acts on the half of the foundation in the side facing towards the inside of the hole, and therefore its weight is represented as a line load along this half of the foundation. The load type is line load in the local z direction with the magnitude of 7.5 kilonewton meters. And here with the ordinates, I can position my line loads. And in this way, the load is placed exactly on the part of the foundation where the floor slab is supported. And here, in this preview on the right, it shows the applied line load directly on the foundation. Now, let's move on to the design situations. For the foundation design, 3 design situations have been created. The first one, ultimate limit state for permanent and transient. Second design situation, ULS permanent and transient for equilibrium limit state. And the third one is characteristic serviceability limit state. And when selecting a design situation, its type is displayed here on the right. And below this, the activate for section define which add-ons use this design situation. And here the checkbox for concrete foundation is activated, and only then is this design situation considered in the foundation design. And each of these design situation is responsible for different design checks. In the first design situation, the add-on performs the reinforced concrete design checks according to Eurocode 2, and in addition, the geotechnical checks for ground failure and sliding according to Eurocode 7. In design situation 2, the design check equilibrium limit state is calculated. And finally, in design situation 3, the add-on check the serviceability related criteria, including load with large eccentricities and high eccentricity loads in core. With this, the loads and design situations for the foundation are fully defined. Let's take a look at the base tab. And here I have activated the combination wizard. And in this way, the load combinations will be automatically generated according to the combination rules of the standards that I here set. Plus, we have here this checkbox, automatically assign corresponding load combinations active. And this is important for the geotechnical design checks, mainly for the ground failure and sliding checks. For the ground failure check, each ULS load combination must be assigned a corresponding SLS load combination, because the characteristic loads are needed to determine the load eccentricity in the effective foundation area. And for the sliding check, also each ULS load combination must be assigned a corresponding characteristic load combination. And for sliding, this is necessarily to correctly calculate the shear resistance. And therefore, this checkbox needs to be activated to perform the corresponding design check. And here in load combination, we can see the generated load combinations. And here in the tab corresponding combinations, we can see for each ULS combination a corresponding SLS characteristic load combination. We are now ready to calculate our stepped foundations. For this case, I go to concrete foundations table, and here I see all the design situations that I have activated for the concrete foundations add-on. And here in object to design, I can see which foundations are active to be designed and which are not. As I said here, the pad foundations in the middle will not be taken into consideration in this today's webinar. Here we can also see the foundation geometry for each foundation. And now we are ready to calculate our foundations. I have already calculated the load combinations, so now RFEM executes directly the concrete foundation add-on. We have a total of 10 nodes with foundation that's going to be calculated. And now we have our results. After the calculation, the foundation results are available in two forms, tabular and graphical. The graphical results are divided into two main lists in the results navigator, design checks and reinforcement. The first list, design checks, shows everything related to the performed design checks. And at the top, it's the design ratio of the envelope. That is the governing value across all design checks and the quickest way to see whether the foundation passes overall. Below this come the geotechnical design checks, divided into ultimate limit state, that is ground failure, sliding, and equilibrium limit state. And then serviceability limit state with the design checks for highly eccentric loading and the foundation rotation design. And then follow the reinforced concrete design checks, also divided into ultimate limit state. Here, bending in X and Y direction, bottom on top, once for the lower foundation slab and once for the first step. Then we got the shear design, the punching shear design. Also here, two punching shear design checks are available. One for the column as the load introduction area and one for the step as the load introduction area. And then we have the detailing. Here are the constructive rules if they were activated in the concrete configuration. The second list is reinforcement. And here it shows everything related to the reinforcement quantities. The required reinforcement shows everything related to the or it shows the analytically required reinforcement area. Then the provided reinforcement is what was entered in the plate reinforcement tab. And then we got the non-covered reinforcement. Here, only the area or the areas where the provided reinforcement is insufficient are shown. And the last option, overlapped required versus provided reinforcement, here overlays both quantities in the same display. These results are also here divided in tabular form into design ratios and reinforcement. The table design ratios on nodes shows for each node and each design situation all performed design checks, sorted here by design situation. At the very top are the design checks from the first design situation, the ultimate limit state. Here all geotechnical and reinforcement concrete design checks are listed one after another. Here we got the ground failure, then the sliding according to Eurocode 7, and then we have the bending failure of the plate in X and Y direction, top and bottom, and then the same bending failure of the stepped foundation or the first step, also in X and Y direction on the top and on the bottom. And then the shear and bunching shear design. And below this followed design situation 2, the equilibrium limit state design, and at the very bottom the SLS characteristic design situation with the 2 design checks. The table reinforcement on foundation shows the reinforcement results. For each foundation, all required reinforcement are listed on the top side in X and Y direction, and on the bottom side also in the X and Y direction for the different design strips. We also here have tables for the provided and not covered reinforcement. And for the both of these tables, reinforcement and design ratios, there is here several sorting options. For example, for the design ratio nodes, we have by design situations, or by loading, or by foundation, or by nodes. The same goes for the reinforcement. We have the required reinforcement by node or also by foundation. Let us now look at the required reinforcement. Here we focus on the stepped foundations of axis A. For this, I have created a corresponding visibility. And here shown is the required reinforcement on the bottom side in the X direction. The individual design stripes are visible here directly on the foundation, each labeled with its value. The highest required reinforcement lies here in strip 2 with 5.74 square centimeter per meter, and here not in stripe 4 under the column directly. And here for stepped foundation, the reason is the effective depth. For example, strip 4 still lies beneath the step and benefits from the full height of the foundation, whereas strip 2 already sits outside the step and can only work with the plate thickness. Exactly. So the values can also here be found in tabular form. For the bottom reinforcement, there is 1 entry per stripe for each direction, and stripes 1 to 4 in the X direction and also in the Y direction. Also mentioning here the top reinforcement, there is no such divisions for the top reinforcement with design stripes, because there the moment is approximately constant over the entire foundation width. So a single reinforcement area is there sufficient. If I want to follow this process in detail, I can open the design check details. And here all intermediate results are listed for each design check. And for the bending design of the stepped foundation, the concept with the 2 design section becomes here clear. For the selected design stripe, here stripe 4, the stripe directly under the column. And here 2 blocks are shown below. The upper block shows the bending design at the foundation slab with the design section at the edge of the first step. And the lower block shows the bending design at the first step plate itself with the design section at the column edge. Both blocks have the same structure, design moment, effective depth, and from these, the analytically required reinforcement area. The direct comparison of the figures is interesting. Here at the foundation slab, there is a design moment of about 127 kN with an effective depth of 464 millimeters. From this results 5.27 square meter per meter. And at the first step plate, the design moment of 200 kN is here higher, but the effective depth is here 864 millimeters. And from this results only 4.44 square meter per meter. And the governing value for strip 4 is therefore the larger of the two. That is 5.27 from the section at the edge of the first step. And this exact value then appears at the top in the line required longitudinal reinforcement area of design stripe 4. And as shown, the required reinforcement can be then displayed graphically on the top side in the X and Y direction, as well as on the bottom side in the X and Y directions. For a quick visual check, the results navigator offers another practical display, overlapped required versus provided. This overlays both values, required and provided reinforcement, in the same image. And the display itself can be switched between 2 views. Here under foundations, we have overlapped values, and we have overlap 3D graphic and overlap 2D result section. The 3D graphic shows the results 3-dimensionally along the foundation, and the 2D result sections is a section plane placed through the foundation and shown as a section. Let us now continue to look at the concrete design checks and start by the bending design. The bending design is performed at both design sections, that is once at the step edge for the plate and at the column edge for the step. And for each of the 4 design stripes, the required reinforcement is compared with the provided reinforcement. Here we can see it on the design check details. And this results in a design ratio per stripe. And the governing in the end is the maximum. And then this maximum is displayed graphically. I would like now to take a look at the punching shear design. And for the step foundation, the punching shear resistance is checked not only at 1, but at 2 locations. And the reason for this is the 2-stage load path. The column load first runs via the column cross-section into the first step, and from there further via the step area into the foundation slab. And at each of these transfer points, punching can in principle occur. And this is why there are 2 separate design checks, which appear as UL2400 and UL2402. We look at node number 1, the first design check, UL2400. Here, the load introduction area is the column cross-section, and the critical parameter accordingly runs around the column with a parameter of U1 equal to 3.9 meter. As the effective depth, the entire structural height is here used. That is step plus the plate together, and we obtain an effective depth here of 858 millimeter. And here from the maximum acting shear force of 336 kilonewton, 2 relieving components are subtracted: the reduced soil pressure within the perimeter, delta VED red with 70 kilonewton, and the component of the compressive stress not relevant for shear with 170 kilonewton. What remains is a reduced acting shear force of 97 kilonewton. This then results in an acting shear stress of about 70 kilonewton per square meter. The resistance is here equal to 1128 kilonewton per square meter, and therefore the design ratio is 6.2. Now we took a look at the second design check, UL2402, concerns the first step plate. Now the load introduction area is much larger, namely the entire step of 1 by 1 meter. The critical perimeter accordingly becomes longer, here 6.36 meter. But in return, the effective depth is smaller, only the plate thickness is here present, and the effective depth is 458 millimeters. And now from the same 336.5 kilonewton shear force, delta VET red is now about 174 kilonewton. Compared to the 70 kilonewton in the other design check, the reduced soil pressure within the perimeter is therefore significantly higher than the other check, because the relieving soil pressure acts over the much larger perimeter area now. And at the end, we remain with 92 kilonewton. And at the end, the design ratio is here 5.8%. Here the punching shear design can also be visualized directly on the foundation. Here the 2 punching shear design checks, UL2400 and UL2402, are available as separate items. And when one of them is selected, RFEM displays the associated punching cone directly on the foundation slab. including the design ratio as a label. Here for UL2400, a compact cone running tightly around the column appears, exactly where the load from the column cross-section passes into the foundation slab. And for UL2402, the cone becomes significantly larger and encloses the entire step. And this makes it possible to follow the difference between the two design checks geometrically. The small cone belongs to the foundation slab, and the large cone belongs to the first step. Here in the navigator, the design checks can be expanded. Below them, you can find intermediate results, which also can be displayed. This allows, for example, VED red to be visualized together with the soil pressure distribution. I can here, for example, switch the display type to isolines, and this makes the soil pressure within the critical parameter much more visible. And in addition to UL2400 and UL2402, there are two more punching shear design checks in the result table, UL2401 and 03. They check the concrete compression strut directly at the edge of the load introduction area, according to section 643 of Eurocode 2. And now I want to come back to again to UL2402. And an interesting situation can be seen here at this step foundation. Here the design ratio is 0. And when I open the detailed results, there's this message. The critical section cuts opposite edges of the foundation plate. Punching design is not required. The shear force will be checked by shear design according to 6.2. So for this foundation, a punching shear design is then geometrically no longer meaningful, and instead the regular shear design according to section 6.2 is used. Here, the critical parameter for punching lies at a certain distance from the load introduction area for the foundation, and this distance is determined iteratively. For a foundation of sufficient width, this perimeter remains completely inside the foundation slat, but if the foundation is too narrow or the perimeter is large, this perimeter extends beyond the foundation edges and intersects them on opposite sides. And in this configuration, a closed punching cone can no longer form. And therefore, the failure mechanism shifts. Instead of a punching or a conical breakout, a shear failure becomes governing. And this is why RFEM switch over. In this case, the punching shear design 2402 shows this error message, and the shear design according to 6.2 appears in the result tables as UL2202, and it becomes the governing design check. And here the shear capacity without shear reinforcement is determined and compared with the acting shear force. So much for the reinforced concrete design checks. Let us now look at the geotechnical design checks. In the ULS, the three geotechnical design checks are the ground failure design, the sliding design, and the equilibrium limit state design. For the ground failure design, I can graphically display the design ratio, then the actions, and then the ground failure, as well as here the failure figure of the ground. Then for sliding, the two horizontal forces as well as the sliding resistance are listed. And this is followed then by the equilibrium limit state design of the structure. Here I can firstly display which edge is involved and in which direction the design check is performed. And this makes it easy to see which edge is governing for the respective design check and how the overturning situation arises. For serviceability, we find the design check for highly eccentric loading. Here, the existing and the permissible eccentricity in the x and y directions are displayed so that the position of the load application points relative to the foundation geometry is easy to follow. For the highly eccentric loading in the core, it is checked whether the compressive force lies within the second core area. Okay, so those were our geotechnical and concrete results. Now we finally can create the printout report. As an example, I display now only the step foundation in the node number 5. And via the button at the top, I can create a new printout report. Here it is possible to save printout report templates and call them up again via this button. For this model, I have already prepared a template, number 16, and I confirm with OK, and then I can confirm with save and show. Then my printout report is then displayed in another window. In this printout report, the basic objects, node types, nodal supports, the boreholes, as well as the load combinations and design situation are here listed. Additionally, I have also here added the additional foundation load table under loads, under the load combination or load case 1 self-weight. And then under the design of concrete foundations folder, I can find here my single foundations, their geometry, and then their design properties, such as the concrete cover, plate reinforcement, the soil properties, etc. And the results folder, we find the individual result tables, such as the design ratio on nodes, the governance reaction by nodes, the provided and required reinforcement by nodes, as well as at the end, the not covered reinforcement by node. Here in the result folder, I have sorted the results by node. Of course, other sorting can be also chosen here. And now I would like to add graphical results to my printout report. And for this, I will be using the multiprint function. In the General tab, I select Multiprint and move directly to the tab Add-ons. And here I have access to all the results of the add-on concrete foundations. I will be using the current view, and here I will select, for example, the punching shear design, the ratio, as well as the red. For the reinforcement, I will be selecting the required reinforcement at the bottom of the plate in X and Y direction, and the same for the overlapped in X and Y direction. Also, we have created graphic templates for our reinforcement layout, and this template, we can find it here, selected. This template can be used here for all foundation, or we can also here specify which foundation in this case just foundation number 1. And here, once again, in the General tab, I can see my graphical results in the preview. Also, I have to select the right printout report and then confirm with save and show. The auto update of the printout is activated, and therefore here I get all the images that I sent to the printout report here with the bunching design and then also the reinforcement. And also here at the end, the reinforcement layout that we created. And with that, I have reached the end of today's webinar. We have seen the complete workflow for designing a stepped foundation in RFEM6, from modeling the foundation and entering the rotated geometry through the definition of loads, all the way to the concrete and geotechnical design checks with their graphical evaluation, and finally the printout report for a clear and verifiable documentation. Thank you for your attention, and back to you, Andreas.
Thank you, Hedi, for your presentation. At the end of the webinar, I have additional hints for you. For example, to our online courses. There is the RFEM6 course. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design. Then the Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. The Eurocode 8 course for the earthquake design. And the AI masterclass course for the use of artificial intelligence. For more information and prices, just scan the QR codes or click at the links here. You can get an RFEM6 course or a Eurocode course for free when you submit your customer project and when we will publish it. You can submit all your files when you scan the QR code or click at the link here. You will reach a form where you can upload all your files. Then a hint to our free online services. There's, for example, the Global community. You can ask questions there, and our support team or other community members will answer you. There's the GeoZone tool for the determination of wind, snow, and earthquake loads. You can, for example, download 3D models, for example, as a template for your project. You can download and install the trial versions of RFEM6, RSTARP 9, RWin3, or RSection. Just try it. You can get more information on our website, blueball.com. You will find our recorded webinars there, knowledge base articles. You can ask the AI assistant Mia 24/7 all the time. That should be also all from my side. I thank you for your attention. Thanks again to Hedi for the presentation. Thank you to Ann-Kathrin for the support by answering the questions. I wish you all a nice rest of the day. Bye-bye.